In the last lecture, we learned how to solve second-order ordinary differential equations when the right-hand side is equal to 0. We call that the homogeneous second-order ODE. In this lecture, we're going to see how to solve a second-order ODE when we have a right-hand side, that is, a non-homogeneous second-order ordinary differential equation. And as we're going to see, the first step in solving a non-homogeneous ODE is to solve the homogeneous ODE. So we're actually going to need to use the skills that we learned in the last lecture. Once we have that part of the solution, we're going to add an extra bit that deals with the right-hand side. Our final solution is actually going to have two parts. We're going to have the homogeneous part, or the homogeneous solution, y subscript h, which solves the homogeneous problem with the right-hand side equals to 0. And we're going to have a particular solution, y subscript p, which is going to deal with that right-hand side. Now we're going to see two different methods for solving non-homogeneous second-order ODEs. The method of undetermined coefficients and the method of variation of parameters. And the method of undetermined coefficients is going to be the one that we go to first. Basically, it involves making an educated guess about the form of the solution with some unknown coefficients and then substituting them into the ODE. The advantage of that approach is that we don't have to do any integration, so it's often a lot faster and easier. If that fails, however, and sometimes it will fail, then we're going to try the other method, the method of variation of parameters, which is a bit more of a technical process, but it can work in situations where the method of undetermined coefficients doesn't work. So we'll describe both of those methods in this lecture, but the first thing that we're going to do is to talk about how and why we have to include the solution to the homogeneous problem in our solution to the non-homogeneous equation. So we're going to prove that. So let's write down what I mean by that. Here's my full differential equation, second order constant coefficients. So a y double prime plus b y prime plus c y, second order ODE with constant coefficients. And that's going to be equals to, we'll call it r of t. So that's a right-hand side there that's going to make this equation non-homogeneous. Now we're going to write down our solution as made up of two pieces. So y of t is going to be y subscript h plus y subscript p, where yh is what we're calling the homogeneous solution. Where that is, it solves the equation a yh double prime plus b yh prime plus c yh is equal to 0. That is exactly the same ordinary differential equation that I started off with, but with the right-hand side equals to 0. This is the homogeneous problem. So we found the homogeneous solution, and we're also going to have another part to my solution. We called it y subscript p, and that we're going to call the particular solution. So again, we're going to show in just a moment how to find the particular solution. That is, it solves the non-homogeneous equation. So with the right-hand side. But the first thing we need to do is to show why I need to include that homogeneous piece. Why do I have to include y subscript h in my full solution? So let's prove that. What I'm going to do is I'm going to simply substitute my full solution into my original differential equation. So substitute y is equal to y subscript h plus y subscript p. So you can see that every time I take a derivative, I'm just going to have to take a derivative of each of those parts. So y subscript h double prime plus y subscript p double prime plus b times y subscript h prime plus y subscript p prime plus c times yh plus yp is equal to the right-hand side, r of t. So this is just substituting y is equal to yh plus yp into my ODE. And if we can show that both sides balance out, then that is indeed a solution. So let's prove that. So if I rearrange all the terms here so that I have all the y subscript h terms, let's underline them in purple. And gather together all the y subscript p terms, the particular solution, underlining them in green. And that's all equals to r of t. You can see that the first terms here, let's put them in purple again, that's just the left-hand side of the homogeneous equation. So we actually saw that that was equal to 0. What does that leave us with? It leaves us with the particular term here, the particular solution. And you can see that that, when I add up all those terms together, is going to be equal to r of t. So what I found is that r of t is equal to r of t. The two sides balance out, and so that means that y equals to the homogeneous part plus the particular part is a solution. So what that means is that I can always add in the homogeneous piece into my solution to this equation to find a new solution. So that means that I have to include it to find the most general possible solution. So whenever we're looking for the solution to a non-homogeneous equation, the first step will always be to find the solution to the homogeneous equation, and then to try and figure out how to deal with that r of t term. So let's take a look at the method of undetermined coefficients, the first of our two methods for finding the particular solution. Now this is basically a guess and check method, or an educated guess method. We're going to make a smart guess about the form of the solution for the particular solution, and then we're going to basically substitute that in and figure out what some unknown coefficients are. So let me show you what I mean by that. We're dealing here with example 1. We have a second order ordinary differential equation. Y double prime plus 5y prime plus 6y is equal to minus 6t plus 25. So this is a non-homogeneous equation. We just saw that the general solution to a non-homogeneous equation is the sum of two pieces, the homogeneous piece and the particular piece, where the homogeneous piece solves the following equation. It solves exactly the same ODE, except I set the right-hand side equals to 0. It's the homogeneous problem. Now we know how to solve problems like that. We assume a solution of the form e to the lambda t, which means that every time I take a derivative, I pull down a power of lambda. I convert my homogeneous differential equation into a quadratic equation for the unknown lambda, and I solve. So let's factorize that. So this has factors lambda plus 3, lambda plus 2 is equal to 0. Something times something is equal to 0, which means that I get roots lambda is equal to minus 3 or minus 2. So these are two unequal real roots, which means that my homogeneous solution is going to be a times e to the first times t plus b times e to the second root times t. Let's put a little box around that. That's the homogeneous part of our solution. And you notice here that there are two unknown constants, a and b, the integration constants, and that will be all of the integration constants that will remain in this problem. Now let's take a look at the particular solution. So yp solves the following equation. So the same left-hand side. But now we have a right-hand side, so minus 6t plus 25. That was our right-hand side for this equation. Now I'm going to solve this by making a smart guess for what yp might look like. So we're going to assume that yp is equal to c times t plus d. Now, why did I assume that yp is of that form? Well, take a look at my right-hand side. You see here that this is an expression that involves a term involving t and a constant term. So I looked at that right-hand side. I'm just going to choose the most general possible solution that looks like that. So I have something times t plus something. Those two somethings, that c and the d, those are unknown constants. They're the undetermined coefficients that we're going to fix by substituting the solution back into my ordinary differential equation. So I'm making an educated guess about the form of the solution with some unknown coefficients that I'm going to figure out by subbing in. So let's try that. Let's see if it works. I'm going to have to calculate the first and second derivatives of yp. So yp prime is just equal to c. Yp double prime is just equal to 0. So substituting into the non-homogeneous ODE, let's write that down again. We had yp double prime plus 5 yp prime plus 6 yp is equal to minus 6t plus 25. So let's put all that in. We found that yp was 0, yp double prime was 0, yp prime was equal to c, and yp we saw was c times t plus d. And we're saying that that has to be equals to minus 6t plus 25. Let's tidy things up. I've got 6ct plus 5c plus 6d. So you can see that on the left and the right hand side of this equation, I've got a term that involves t, and I've got a term that's a constant. Now, this has to be true for every possible value of t, so I can match the corresponding coefficients on the left and the right. So match the coefficients of each function of t, independent function of t. So you saw that there was two terms there. There was a function just t, something times t, and I had a constant. So that if I match the purple terms, I have to have that 6c is equal to minus 6. And if I match the green terms, you see that I get 5c plus 6d is equal to 25. So I've got two equations for two unknowns, c and d. I can solve these simultaneously to figure out what those two coefficients are. I can immediately solve the purple equation, so c is equal to minus 1. Let's substitute that into the green equation. So I've got 6d is equal to 25 minus 5 times c. c is equal to minus 1, so that's 25 plus 5, or 30, So it gives me that d is equal to 30 divided by 6 is 5. So what I found is that my particular solution, we said that was c times t plus d, is equal to minus 1 times t plus 5. That is the form of the solution that correctly balances or satisfies my non-homogeneous ordinary differential equation. So this isn't the full solution, of course. I still have to include the homogeneous piece. So yt was equal to the sum of the homogeneous solution and the particular solution. We found that the homogeneous solution was a e to the minus 3t plus b e to the minus 2t, and the particular solution was minus t plus 5. The last part of this problem asks us to find out what happens in the steady state, that is the long-term behavior of this solution. So what happens as t gets really big? Well, you can see that I've got a couple of different pieces here. I've got an e to the minus 3t, I've got an e to the minus 2t, but both of these terms are exponentially decaying. They decay really fast. So as t goes to infinity, those two terms will tend towards 0, whereas this term is heading off towards minus infinity, and this term here is staying constant. So the long-term behavior is going to approximately go as minus t plus 5. Now, an important question here is, how did I know how to choose the form of my particular solution? This guess that I made here that then allowed me to figure out what the unknown coefficients were, c and d. Now, the way I did it was just by looking at the right-hand side and choosing the most general possible form of my particular solution that kind of looks like that. Another way to think about it is that when we're substituting this solution into my ordinary differential equation, what I'm going to do is take a whole bunch of derivatives. So when I form my particular solution, I'm going to make a solution that looks like the right-hand side and its derivatives. So let's take a look at some different examples of that. So for example, if my right-hand side r of t was equal, or r of x in this case, is equal to 3e to the 4x, I'm going to look at that's a possible yp that involves this expression and all its derivatives. Its first derivative is just e to the 4x. It would pull down a constant, but we don't care about the constants. Second derivative would also just be something like e to the 4x. So I only ever get e to the 4x. If I start off with an exponential, I'm always going to get back an exponential with the same number 4 appearing up here in beside the x, multiplying the x. So the choice that we should make for the particular solution, our guess, when I have something that looks like this, should be something like e to the 4x. Another example might be x cubed minus 7. So this is a cubic expression. So I might try and pick a particular solution that is the most general possible cubic expression. So ax cubed plus bx squared plus cx plus d. Another way to think about that would be I should include all the terms that appear here, so x cubeds and constant terms, and all the derivatives. So one derivative gives me x squared, another derivative gives me terms that depend upon x. So I need to include terms x cubed, x squared, x, and a constant. Likewise, we could think about sine 4x. Every time I take a derivative, I get out something like cosine or sine. So I should form a general solution that has the form of cosines and sines, so the almost general possible trig solution, that has the same frequency. Notice that the 4x appears here and the 4x appears here. I don't include something that looks like 4x and 17x. That wouldn't make any sense because I could never get something that looks like 17x if I start off with 4x. What about if I have things like combinations or products of terms? I've got an exponential here and a cosine. Well, you can see that if I take a bunch of derivatives, I'm only going to get exponentials and cosines or sines. So the most general possible guess would be something that involves cosines multiplied by exponentials and sines multiplied by exponentials. Likewise, if I start off with something like a quadratic multiplied by an exponential, the most general possible right-hand expression here would be an exponential multiplied by a quadratic. So there's a full list of the possible solutions or possible guesses in the written notes, but the general rule of thumb should be that you need to create the most general function or combination of functions that could be related to my right-hand side or its derivatives. So let's take a look at another example and see what happens. So in this example, we've got another second order differential equation with the right-hand side equals to 55 e to the 2x plus 3x squared plus 14. So this is some sort of combination of exponentials and a quadratic expression. We're also given some initial conditions here, and we're going to use those to figure out what the constants of integration are. So as always, when we're forming our solution, we're going to form it in two pieces. We're going to have a homogeneous piece plus a particular piece, where the homogeneous piece solves the homogeneous problem. Just set the right-hand side equals to 0. Now we can easily solve that by writing down the auxiliary equation right away. Every derivative gets turned into a power of lambda. So I've got a second derivative, I don't have a first derivative, and I have no derivatives. So I've got lambda squared plus 1, that has solutions. Lambda is equal to plus or minus I. So this is two complex solutions, in fact two imaginary solutions. There's no real part. If you like, I could write that as 0 plus or minus I. So that means that my homogeneous solution is e to the real part times x, a cosine of the imaginary part. So that was 1 times x plus b sine of 1 times x. Of course, e to the 0 is just 1, so this is going to give me a cosine x plus b sine x. So that's my homogeneous solution. Let's go take a look at the particular solution. So ypx solves the full non-homogeneous differential equation. So we said that that was 55 e to the 2x plus 3x squared plus 14. Now I need to choose or make an educated guess for what that particular solution might be. So what should we choose as our guess? Well, we see that we have an exponential here, e to the 2x, and whenever I take a derivative of an exponential, I just get back an exponential. So I should include a term, it's called c e to the 2x, to deal with that exponential term. I also have a quadratic term here, so I should include something that's the most general possible quadratic, so something like dx squared plus ex plus f. You notice there I've got x squared, x and f, even though x doesn't appear in the right-hand side. If I took a derivative of this, I would get an x. So I need to include an x here as well. We always need to include any terms with a power smaller than the highest power of our polynomial term, right? Because I can always get those terms by taking a derivative. And we need to choose a particular solution that is the most general possible function that looks like this term and its derivatives. So there's actually 4 unknown coefficients here, and we're going to have to match them by substituting this whole solution into my differential equation. So let's build up a little table with the first and second derivatives. So e to the 2x, if I take a derivative, I've pulled down a factor of 2. Derivative of x squared is 2x. Derivative of x is just 1, and we get rid of the f term when I take a derivative. Second derivative is equal to pulling down another factor of 2 plus 2d times the derivative of x is 1 plus derivative of e is 0. So let's put all this together now. Sub this into my non-homogeneous ordinary differential equation. That's going to give me y double prime, so 4c e to the 2x plus 2d. So that was y double prime. We have yp, so that was c e to the 2x plus dx squared plus ex plus f. So this is plus yp. And all of this has to be equals to my right-hand side. So 55 e to the 2x plus 3x squared plus 14. So this whole thing here is r of x. So this expression here, when I gather all together all the like terms, is actually going to give me 4 equations for 4 unknowns. I'm always going to get the same number of equations as unknowns when I use this method, because there's always going to be a term involving e to the 2x, a term involving x squared, x, and a constant. There's always going to be enough equations for each of the terms that appear, each of the coefficients. So let's gather together all the terms involving e to the 2x and make them equal to one another. So I get 4c plus c equals 55. Those are the coefficients of the terms involving e to the 2x, e to the 2x, e to the 2x. What about the terms involving x squared? Well, there's a term there, and there's a term here. So let's put those together. So we get d equals 3. So that's what we get when we match all the terms involving x squared on the left and on the right. So dx squared is equal to 3x squared, so d is equal to 3. What about the terms involving x? Well, we only have one of those, so that means that e has to be equals to 0. The only term involving x on the left-hand side is e, and there's no corresponding term on the right-hand side, so that means that e must be equal to 0. Last one, the terms involving constants. So there's a 2d there, there's an f, and there's a 14. Those are all the constant terms. So let's gather those together. I've got 2d plus f is equal to 14. So you see that I've got 4 equations for 4 unknowns. In fact, 2 of these equations actually give me right away solutions for 2 of the unknown coefficients, and I can use those now to solve for the other ones. In fact, this one also gives me a pretty simple solution. So let's start gathering together my solutions. 4c plus c is 5c is equal to 55, which implies that c is equal to 11. We already have that d is equal to 3 and e is equal to 0. The last equation was 2 times d plus f is equal to 14, or f is equal to 14 minus 2 times d, which is equal to 14 minus 2 times 3, which is 6. So f is equal to 8. So again, we use the yellow equation there for that. The orange equation is e to the 0 equals to 0. The red equation is this one. And the pink equation is this one right here. So now I actually have all of the undetermined coefficients appearing in my particular solution. So let's put those in. I had c e to the 2x plus dx squared plus ex plus f. We figured out that c was equal to 11, d is equal to 3, e is equal to 0, and f is equal to 8. So that is the particular solution that satisfies my ordinary differential equation. Now remember that we need the full solution, which is the sum of the homogeneous part and the particular part. So we saw that the homogeneous part was a cosine x plus b sine x. And we've just found the particular part, which was 11 e to the 2x plus 3x squared plus 8. Now the last part of this problem involves figuring out what those coefficients a and b are. Remember, those were the integration constants that came from the homogeneous problem. And whenever we're dealing with the method of undetermined coefficients, we will always fix whatever undetermined coefficients appear in the equation for the particular solution, but we're still going to have those unknown constants, integration constants, coming from the homogeneous problem. And we have to have those because this was a second order ordinary differential equation, and we saw that whenever we're solving an ODE, we get unknown constants equal in number to the order of the differential equation. So this is a second order equation. I have to have 2 unknown constants that I have to fix then using some additional information, some initial information. And we're told in this problem that we're told that y at 0 is equal to 20 and y prime at 0 is equal to 28. These are initial conditions. And we're actually going to use these now to fix a and b. I couldn't do that, of course, until the very end of this problem because I didn't know what the form of yp would be. So now that I have that, I can figure that out. So let's put in y at 0. We saw that that is equal to 20, so let's substitute in x is equal to 0 into my solution here. So I've got a times cosine of x, that's a times 1, plus b times sine of 0, which is 0, plus 11 e to the 0, plus 3 times 0, plus 8. E to the 0, of course, is just 1, so I have a plus 11 plus a 18, which is a plus 19. So that gives me that a is equal to 20 minus 19, which is 1. What about the initial condition for y prime? Well, that's obviously going to depend on the derivative of this, so let's find the derivative. Derivative of cosine is minus sine. Derivative of sine is cosine. E to the 2x is going to bring down a factor of 2, so I get 11 times 2. derivative of x squared will give me a factor of 2 as well, so I get 3 times 2 plus derivative of 8 is just 0. So this is the derivative of our solution. Let's now put x is equal to 0 into this and use the initial conditions. So we have y prime at 0 is equal to 28, we're told. Putting in x is equal to 0 in here is going to give me minus a times sine of 0 is 0, plus b times cosine of 0, so that's 1, plus 22 e to the 0 plus 6 times 0 is 0. So I get b plus 22 is equal to 28. So that means that b is equal to 28 minus 22, which is equal to 6. So putting all of that together then, we have the solution y is equal to cosine x plus 6 sine x plus 11 e to the 2x plus 3x squared plus 8. So we managed to fix all of the unknown constants now in this expression using the initial conditions. So there's again a couple of general comments about the method of undetermined coefficients. On page 22 of your additional course notes, you'll actually find a list of trial solutions. But in general, the approach should be that you find the most general solution that could possibly satisfy the differential equation. If we have any combinations, for example, sums or products of different functions, then the corresponding trial solution will be a sum or product of trial solutions. And one last thing that we actually haven't had a look at yet is what happens when I have a trial solution which is already a solution of the homogeneous problem. We're actually going to look at this in a bit more detail in the next lecture. But in that case, we actually have to generate a new solution by multiplying by x. So if I come up with a trial solution that's already dealt with in the homogeneous solution, I can't just use that solution again. It wouldn't give me anything new. I need to generate a new solution. So again, we'll talk about that in the next lecture. The last part of this lecture we're going to spend talking about the method of variation of parameters. This is another approach that we can take to solve for the particular solution if the method of undetermined coefficients doesn't work. Now this is definitely a much more involved technical process, so it will take a lot more time to work through. So if at all possible, use the method of undetermined coefficients first, but if that fails, then this is at your fingertips so you can use. Now the proof of this formula is actually given in your course notes, but the way that we're going to do it is as follows. If I have some general second order non-homogeneous differential equation, and in fact I am going to include the possibility that, that this has got non-constant coefficients, so I've got coefficients in front of y prime and y that are functions of x. So this is a general second order ordinary differential equation with the right hand side. And let's say that we have somehow found the homogeneous solution. So setting the right hand side equals to 0, we found the homogeneous solution. And it's of the form some constant times y1 of x plus some constant times y2 of x. So like in the last example, we had a cosine of x plus b sine of x. Then those would be our y1 and our y2. Then we're going to form our particular solution by creating or building this. So this is involves integrals over our solutions times the right hand side and divided by this function w of x, which is the determinant of this matrix. Now there's a lot going into this solution here, so the best way to illustrate it is by actually working through an example. So we're going to use the method of variation of parameters to solve the differential equation y double prime plus y is equal to the secant of x. And just in case you don't remember what that is, it's 1 over the cosine. So the first step in this is always, always, always solve the homogeneous problem first. So look for the homogeneous solution. That is the solution to the equation y double prime h plus yh is equal to 0. So this is actually the same homogeneous problem that we solved in the last example, but let's work through it again. We're going to write down the auxiliary equation or characteristic equation, which is the equation we get by replacing every derivative of y with a power of lambda. That gives us a quadratic equation for lambda that has solutions lambda is equal to plus or minus I, which means that my homogeneous solution is going to be a cosine of x plus b sine of x. So again, exactly the same as we had in the last problem. Now we're going to write this as a times y1 of x plus b times y2 of x. So we've found our two homogeneous solutions, y1 and y2. And we're going to use the method of variation of parameters to find the particular solution. So let's take a look back at the formula. You see that it's going to involve some integrals, and I'm going to need to calculate this matrix, the determinant of this matrix, W. So let's form that matrix and find its determinant. So we said that W is equal to the determinant of the matrix y1 of x, y2 of x, and its derivatives. So let's put the derivatives in. So y1x prime is minus sine. The derivative of y2 is cosine. So if I put all that in here, I'm going to get the determinant of the following matrix. y1 is cosine, y2 is sine. Derivative of y1 was minus sine, and the derivative of y2 was cosine. So the determinant of that is just going to be cosine x times cosine x minus sine x minus sine x. So that's going to be equals to cosine squared x plus sine squared x, and we know that that is equal to 1. So our matrix W, our function Wx is equal to 1. We're now ready to form our solution. So the particular solution yp of x is equal to minus y1 of x times this integral of y2 f of x all over w plus y2 of x integral y1 f of x all over w. So it's a complicated formula, but the good news is that we would give it to you in an exam if you needed to use the method of variation of parameters. So you just need to be able to use this formula. Alright, so what I'm going to do here is split this up into two pieces. I'm going to write this as minus y1 of, we'll call this integral 1 of x, and I'll call this integral 2 of x, and then we'll put it all together at the end. So let's write that out. Integral 1 of x is going to be given by integral of y2 times f of x all over w. And we have all those pieces now. y2 is equal to let's have a look back up here. y2 was sine of x. F of x is simply the right hand side, it's 1 over cosine, and we saw that w of x was 1. So I have all the pieces I need. Let's put it together. y2 is equal to sine. F of x is 1 over cosine. W is just 1. So you can see that this actually turns into the integral of tan of x. That's actually one of your tabled integrals. So that's the natural logarithm, absolute value of secant of x, or if you like, it's minus the natural log of cosine of x. Remember, secant x is 1 over cosine, so that would give you a minus sign for the natural log. So that's in your tables. What about the other part? I2 of x, that integral was the integral of y1 times f all over w. y1 was cosine, f of x was 1 over cosine, and w was 1. So we actually find that this is very simple. We get cancellation of the cosines. We're taking the integral of 1. So we end up with x. So I2 is equal to x. So now let's put all that back together again. I've got the particular solution is going to be equals to, if I look back at my formula, I said it was minus y1 times I1 plus y2 times I2. So we've got to get that minus sign in there. We got minus y1 times I1 plus y2 times I2. y1 was cosine. We saw that I1 was natural logarithm of the secant, or minus the natural logarithm of cosine. y2 was sine of x, and I2 was just x. Let's put that in front. Here's my particular solution. And so the full solution is the sum of the homogeneous piece and the particular piece. So that is a cosine of x plus b sine of x. That's the homogeneous part. And we have the particular solution. So plus cosine x times log of cosine of x plus x sine x. And a good exercise would be to check that this actually is a solution by substituting it into subbing into the ODE. Just make sure that both sides balance each other to make sure that you do in fact have the solution. But that's the method of variation of parameters. And again, this is definitely a bit more complicated. It involved doing some integration, and in fact we needed to use a tabled integral to find the particular solution. And in general, our strategy with solving ordinary differential equations will be to avoid integration whenever possible. So this is definitely something that you would only use as a last resort, but it's there for you if you need it.